Hi, everybody. Hi, everybody. Welcome to CBE. Thanks for that introduction, David. My name is Paul Raftery. I'm a staff researcher here at CBE. And today I'm going to be talking about existing buildings and how we can reduce natural gas consumption in that building stock. So this is part of a much larger California Energy Commission funded research project that was focused in on the space heating and hot water systems in these buildings. And the reason we focused in on that is because it's by far the largest gas consumer. Relatively little in large commercial buildings is used for like domestic or service hot water. Most of it's for space heating. And this project was pretty large. It had a broad scope. Some of you may have seen me speak about this or aspects of this in past meetings, but we were measuring performance and losses from these components in both the lab and the field. We were gathering data and analyzing it from literally hundreds of buildings nationwide. And then we were also going out into real buildings and demonstrating how you could do reductions in a couple of different sites. And today I'm going to be talking about the two primary demonstration sites that we had for this project. So this is just a quick overview of the two existing buildings. They're both large office buildings, under 20 years old. And when the project started, they had an existing single non-condensing boiler. They had distributed chilled water system. And then they had two air handlers, each serving about 200 VAV zones, most of which have hot water reheat. At a very, very high level, the efficiency measures were we brought the existing controllers up to ASHRAE guideline 36, so kind of a standard set of control sequences that represents current industry best practice. And then we replaced the existing boilers with very small high turn down boilers. That project was planned to happen anyway, so it was the kind of end of life redundancy project. So we were leveraging that as part of this with our partners, the building owners. Now, it's important to note that the controls work we did here was really in-depth. Though we didn't replace the existing controllers throughout the building, we did go down to every single individual zone level and fix everything we could without replacing the controllers. So we corrected zone minimum airflows, we identified and fixed passing valves, we capped bypasses at the zone level. Up at the air handler, we not only made sure that there were resets for like supply air temperature and hot water temperature, but we actually made sure they were working correctly and then used trend data to basically ensure that they're resetting over a really wide range of temperatures, much wider than you would normally see. So for example, these buildings were designed and operated to 180 Fahrenheit supply water temperature. In the post-retrofit condition, the maximum temperature they run at is 140, and they sometimes reset as low as 90 Fahrenheit supply water temperature in the summer in an existing building. So we really went to a lot of detail before we replaced the boilers. And then when we replaced the boilers, we put in really small high turn down equipment. And the results show really large natural gas savings. This is the PG&E utility bill meter. This is daily gas consumption on the y-axis. And then in the x-axis, we have the average outdoor temperature on that day. And the blue line shows the pre-retrofit condition before we did anything. And then the yellow line shows the post-retrofit condition, which is both the effect of the boilers being replaced and the controls retrofit. Overall, this is a 71% reduction in natural gas savings annually on this building. We had a second building. We saw 69% gas savings in this with a slightly higher base load in that building. So overall, we're seeing really huge site level emissions reduction here. 70% of the scope 1 emissions of these buildings was cut by this measure, it's combined measures. On the electricity side, we also saw savings, but those are a little bit more hard to quantify because we had to rely on submeter data that was installed after the boilers were operational, which is also in the middle of the pandemic, so it's a little bit messier. But as best as we can tell, there's about a 20 to 25% electricity savings on the fan energy and a 40% chilled water savings on the building where we had the meter to quantify that. Overall, the estimated utility savings are over $100,000 a year, or about 50 cents a square foot per year from the combined set of measures. So it's super clear to me that if we want to really reduce emissions in the existing building stock, we should be going out and doing this at scale in every building. And I hope the portfolio building owners in the audience are looking at this and going like, how can I leverage this, and come talk to me afterwards. But if we wanted to reduce emissions further in these specific buildings, these two specific buildings, what would we do? So we also looked into that. And of course, the answer is you would electrify to further reduce natural gas consumption by installing a heat pump to service that heating load. And there's always a question about how large that heat pump should be. So this is one of the things that anybody who's working on these projects faces. And you have to consider things like first cost and operational cost, space, weight constraints for a roof that wasn't necessarily built to support the weight of an air-to-water heat pump, service capacity, embodied carbon of the equipment and the refrigerants. And I wanted to kind of walk through some of those decisions and look at what that would actually look like for these two buildings. So this image here is the satellite image of one of the rooftops, and the footprint of the two new boilers is there in orange. This is what an air-to-water heat pump would look like if you were to fully electrify that while maintaining the exact same capacity as those two new boilers, which are very aggressively sized. So we also wanted to look at a partial electrification option here, and that's the footprint of an air-to-water heat pump that's 14% of the boiler capacity, and that's at the heating design day condition for this location. That corresponds to actually being able to serve about 20% of the peak measured load in the building, because there is a little bit of a redundancy requirement for the actual site. But the really interesting thing is that that tiny little heat pump can actually electrify 77% of the annual heating load in these buildings. And that's for a couple of reasons. One is because most of the time heating loads are really low, so you just don't need that capacity. And then on top of that, as it's warmer outside, when you move away from those heating design day temperatures, heat pump capacity also increases. So when you combine those two things, you end up with a huge amount of the load annually that can be electrified. And there are other considerations, mainly that electricity grid emissions vary with time. Here you're seeing an actual real day just this year in February, and the x-axis is time, and the y-axis is the grid marginal emissions. These are the short-run emissions. So the way I think about this is, if I was going to consume 1 more kilowatt hour of electricity right now, what is the generator that would be responding on the grid by increasing its output? And as you can see, in the middle of the day, it drops down because California has a pile of solar on the grid. Now, layering on the measured load in this actual real building, you can see that is the red line. And currently, that's being serviced by a gas boiler. If we had that tiny little heat pump, it wouldn't even be able to meet the load on a February day, not to mention on a design day. You can see it's maxed out there, that little blue line. But you might also notice that the times when you have a lot of heating, in this post-retrofit condition where we fixed up all the controls and got rid of all the simultaneous heating loads that shouldn't be there in the first place, the times that you have the remaining heating generally correspond with high grid emissions hours. It's winter mornings when the sun isn't up. On top of that, it's colder temperatures, so your heat pump is less efficient and it has less capacity. When you layer all these things together, when you look at the actual heating emissions from this actual real system and then the two alternate cases, you see that there's relatively little emission saving on today's grid right now from this particular intervention at those particular times of day. You do see savings from partial electrification and you do see savings from full electrification, but at that specific point in time, they're not as large as many people would expect. And stepping back for a second before we show the annual results, we saw enormous emissions reduction potential with an operational cost savings from a deep energy retrofit measure. We saw 70% on-site natural gas reduction and 50 cents a square foot per year of energy savings. If we do that first and focus on that at scale, it will make electrification of the building stock easier because you'll have smaller equipment, and it will put less stress on the grid when you go and electrify because there'll be less loads on the grid too. So on the right, you're seeing the annual estimate for the actual emissions from this building just normalized per hour. And you can see the pre-retrofit and the post-retrofit case. On today's current grid, we do still see substantial emission savings from electrifying, even on the grid right now. That's not to mention what will happen over the lifetime of the equipment. But there's not much of a difference between the partial electrification case and the full electrification case, after assuming you've done the efficiency measures first, and that is a big assumption. But the big difference here is that the partial electrification comes at a fraction of the first cost, a fraction of the embodied carbon and refrigerant and general environmental impacts of doing so. And maybe more importantly, for some of the current equipment on the market, the actual heat pump equipment itself will be operating at more uniform capacities and probably at higher performance rather than cycling, which you would have if you had a huge air-to-water heat pump up on the roof there. Looking out further to California's commitment to have a fully clean grid by 2045, you can see that even in that scenario, partial electrification gets you 95% of the way to emissions reduction compared to the pre-retrofit state in this particular building. So we can get a huge way there by going through partial electrification. But it's important to recognize that we got the biggest chunk by efficiency measures that are much less invasive, and we should be doing that at scale. And that's really what I learned in this project, is that there's way more emissions reduction potential out there from in-depth efficiency retrofits than people are internalizing and thinking about at policy levels, at building owner portfolio levels. This is the way you can save serious emissions, and we should be doing that first, and then electrifying should be our priority. So I won't go into these points in detail, but if you are working on these projects and looking to kind of repeat this or scale this, we did, as well as the actual demonstrations, we developed a couple of screening methods and applied them in some studies to help identify buildings that would be really good candidates for a similar retrofit. Basically, what you're looking for is large, oversized, or poor turn-down boilers in the existing building, indications of significant controls problems like incorrect VAV and minimum airflow rates, or heating plants that run 24/7 and don't reset to really low water temperatures in the summer. Those are all great indicators that there's a lot of savings here from relatively low cost measures. Another one you can do is, if you don't even have any mechanical information about the building at all, and you just have the gas bill data for each month of the year, if you have an office building that's consuming a decent amount of natural gas in the summer months, chances are there's a substantial energy savings there, because realistically, if you're seeing that and there's no gas consumer on site other than a HVAC system, it's very likely that you have a problem with controls, either at the boiler or the air handler or the zone, or all combination of those. So with that, I'd like to just close out to say that we've lots more information on the site, and there will be more resources added as soon as the CEC reviews and lets us publish them on the website. And if you want any copies of any of the kind of pre-publication drafts, we can share those with you now. And we will be talking about this with a couple of other industry partners, Megan and Stet, diving into existing building retrofits, all electric new construction, and central plant design, looking to decarbonize that building stock as effectively as we can. So with that, I hope if you've interest, you'll also ask questions or join the breakout session. And thank you for your attention.